Hi everyone, how are you doing? My audio and video, everything is fine, right? Okay, so let's get started. Now, today we are going to start a new topic, which is conditional expectation. So, by the way, how many of you have seen the previous lectures? There was one lecture regarding the, recursive expectation, the tree method, right? Tree method of expectation you have seen. How many of you have seen that lecture? Let me know. Okay, that was from module one, right? So it was module one. For example, there were we were growing a tree. So either you can grow till infinity, you can stop in between, like that, right? So we have seen two or three ways to explore this tree. So you have seen this lecture, right? Okay, great. So this was a lecture which we have already seen. Now we are going to formalize this. Okay, so basically, instead of having the only the intuition, so we have seen the intuition, which was definitely necessary, but now we are going to have the mathematical justification of these things, right? What we have already seen. So we have divided this particular topic into two parts, which is two lectures basically, which is first is conditional expectation, next is total law of expectation. Okay, so let's just first see this conditional expectation in bit more detail, and then we will see in the next lecture we will see, okay, something called as total law of expectation. So yeah, just a second. So let me just write it here, that in the next lecture, we will see something called as total law of expectation. Okay. Okay. This is a small topic, but let's just see this. Uh, Now, do you remember, from the earlier, discussions, do you remember what is the formula of expectation? Let me know. Most probably you might remember this, right? So the formula of expectation looks like this. The formula of expectation looks like this. How many of you remember? Okay. So which means that if you want to find the expectation of any random variable, let's suppose y, then this expectation will be y into probability of y being any number, let's suppose a small y, right? And then you are going to sum of all the possibilities of y. Okay. This is the formula to find the expectation. Okay. Formula to find expectation. Now, let's just see how to find conditional expectation. Okay. So expectation is okay to everyone. Now, let's just see how to find conditional expectation. So basically, conditional expectation is defined something like this. Okay. So the way we have defined the expectation, in the similar way, we are going to define the conditional expectation. For example, the expectation was defined like this. Okay. So here I'm saying expectation of y equal to this, something like this. Now, for the conditional expectation, what we can do, we can put the condition on an event. Okay. For example, condition on event A, right? So we can put the condition on any event A. So you can say that this is the expectation formula and this is the conditional expectation formula, right? So this is conditional expectation formula, which means the only change that we need to do is that instead of writing it as just a expectation, we are conditioning on some event. Okay, event A. So this is some event A. So the difference will be that earlier we were using what we call it. Do you remember what we call it? What kind of probability we call it? It is joint probability. It is marginal probability. It is conditional probability. Yes. So Rajeshri is saying it is marginal. Yes. So this is marginal probability, right? So we earlier we have been using marginal probability. Now we will be using the conditional probability. This is the only difference. Which means if I write both of the formula, right? at the same page, then you can say something like this. See here that this is the conditional expectation that we have, and the exact similar formula we have for the normal expectation, which means that if you want to write the expectation, then you will be just removing these conditions. Let me know if the formula at least is okay to everyone, right? Okay, great. Now, these are the two formulas that now we know. Now, let's just understand this formula, that what it is trying to say, okay? This new formula, this is the new to us, right? This is already old. This is the old one. This is something new. This is something new to us. Let's just try to understand this, okay? That what it is trying to say. So what it is saying, that expectation, expected value, okay, expected value of any random variable y, given that given that there is some event a, right? Then what is that value? The expectation with respect to that some event has already occurred. Then in that case, we will be using the conditional probabilities, okay? So earlier we were saying the expectation of y, and irrespective of any condition, then we were using the marginal probability, right? Earlier we were doing like this. Now if they are saying that okay, some event has already occurred, then in that case I will be using the conditional probability. That is the only difference. Now you can say this is kind of, event. You are having the event here, right? I mean, you need to have the event only, but you can say this is event version. Okay. Now, instead of writing this age and event, you can also write a random variable, which means you can say some random variable here. For example, you can say, let's suppose, do you know what is the relation between random variable and an event? So suppose I want to write some random variable as a form of event. So how can I write it? Yes, great. So Samir is saying x equal to something. So this is one of the thing, right? X equal to small x or small c or whatever. Like if you're comfortable with a small c, let me just write a small c. Okay. So this is, you can say, random variable version. Okay. I mean both are the same, but just a way of looking it. Okay. So this is event version. I mean, there is some event condition on event, and you can also write the event as in random variable form. So just I'm calling it random variable version. I mean, these are not my names; these are standard names. Okay, these are. It's not like that. I'm coining those terms. These are already standard terms, right? So these are the. I mean, you can say this is just one formula. This is the formula for conditional expectation. Let's just see that what it is trying to say. Okay, so let's just see with some example. So suppose, let's just see this example. Okay. Suppose that I have a pair of okay, I have a die which I'm rolling twice, right? Now let's suppose I want to find out, right? I want to find out the expectation of some expected value of some, such that there is the condition of that is that there is no six. Okay. So expected value of x, of the sum, such that there has been, okay, no six on any dice, which means that what are the possible value of the first dice that you can get. The possible value of the first dice is 1 2 3 4 5 6, right? The possible values of the if you are rolling it twice, then the possible value that second time it may get 1 2 3 4 5 6. Now they're asking, let's define a random variable sum, okay, which is x plus y. They're asking that what is the expected value of x plus y, given that given that there has been no six. Okay, there has been no six. Okay, so now let's just try to see that how we can solve this particular question, right? So you can do one thing, you can directly apply the formula. Okay, let's just try to apply the formula. So what is the formula? See, the formula is saying that expected value of any random variable, okay, any random variable. For example, you can take it, let's suppose z. Okay, expected value of let me write, instead of x and y, can I use something else maybe? Okay. So let's just see. Okay, let's just call it Z. Okay. Given that any condition, okay, any event. So let's suppose this is A. Then what was the formula? Or maybe I can directly copy the formula from here. So this is the formula that we have. So we have the conditional probabilities here, right? Okay. So this is the formula that we already know. Now let's just try to apply this formula and let's just see what is the answer we are getting. Do you want to try this? So expected value of sum such that there is no 6, right, is equal to summation over the what is the possible values of sum? What is the possible values of sum? Tell me. Yes, 2 to 12, right? This is 2 to 12. Okay. So you can say that anything, okay? Some, let's suppose this is C equal to 2 to 12, right? And then C into, or maybe if you don't want to use C, then let's just use some other variable. Let's suppose S, okay, small s. Small s into probability of probability of sum equal to small s given that there is no 6. Is this formula okay to everyone? Okay. Now just find out this. So the probability of sum equal to, let's suppose, 2 such that no 6. So what is the probability? Tell me. Or maybe I can do one thing. I can, make a table. So for example, if the this is the outcome of first dice, okay, outcome of first dice. Let's suppose these are the outcome of second dice, which I'm calling y. Let's suppose this I'm calling x. So let's suppose these are the values 1, 2, 3, 4, 5, 6. Okay. Here also I have the similar values, which is 1, 2, 3, 4, 5, and then 6. Okay. Now suppose I just, have the partitions. Okay. Suppose these are the values that I have. Now, what is the value of x plus y here? The value of x plus y will be 2. What is the value of x plus y here? I think 3. This is 4. This is 5. This is 6. This is 7. Right? Okay. Now, this is 3. This is 4, 5, 6, 7, 8, and so on, right? You can fill this table. So these are the, let's suppose, values of sum. So what is the probability that so they are saying what is the probability that sum being, let's suppose, 2, there is no 6, right? So what is the probability that sum being 2? Which will be, this will be, you can write it like this. So what you can do, if there is no 6, then you can do little smartly. What you can do, you can not even consider this particular this particular row and this particular column. Is this okay to everyone? If we don't even consider these things. Okay. Now, if you don't consider these things, now which means that you have the reduced domain. Do you remember that in the conditional probability, I motivated the idea using the reduced domain also? Okay. Sometimes it is better to work with the reduced domain. Do you remember that? Now, right now, given that how many of these numbers are there? I think this is 5 cross 5 grid. So how many are the possible values of the sum? I think I think you can say 25, right? 25 are the possible values. Okay, I mean this is a 5 cross 5 grid. Now, what is the probability that sum being 2? What is the probability that sum being 2? This is equal probability, right? This is 1 upon 25. Great. Great to see that you people have answered this. Okay, this is 1 upon 25. So Diksha, Rastri, Sonamatta. So everyone has answered this. So it is really great to see. Okay, because I mean, it really makes me feel better that you have already, done your basics very correctly. So these are the probabilities for any of this you can say the cell, right? So which means the probability that the sum being 2 is 1 upon 25. Now some of you might be getting confused that why it is not 1 upon 36. How many of you might be are getting confused that why this is not 1 upon 36? See, 1 upon 36 could have been there if you're considering this and this. But now you are in the reduced domain, right? In the reduced domain, right? Or in the reduced sample space, you can say, in this reduced sample space, everyone is equally likely, right? Everyone is equally likely in the reduced sample space. So that's why we are saying 1 upon 25. Why? Because every outcome of sum, every outcome you can say, or every value of the sum is equally likely in the reduced sample space, right? Outcome is equally likely in a reduced sample space. Okay. Now if you're still confused, let's just see how to do it mathematically. Okay. For example, probability of sum being sum being 2, given that there is no 6. This is what we want to find, right? Intuitively, how much it is? Intuitively, what do you think? It is 1 upon 25. This is, let's suppose, intuitively you got it, okay? Intuitively you got it, right? Right? Now, let's just see if we can get it mathematically also. In the sense that if we don't use the reduced domain, instead of intuitively, let me just write it using the reduced domain, right? Using the reduced sample space. Okay. Now let's just see how to do it mathematically. In the sense, the probability of sum being 2 and, okay, and there is no 6 divided by probability of there is no 6. Okay. So, so what is this probability? There is no 6. What is this probability? See, these are the 36 pairs. If there is no 6, so I think there are 25 pairs in which there is no 6, right? So I think this is 25 pairs where there is no 6, right? Divided by 36. Okay. Divided by 36. Now, what is this probability? Sum being 2 and there is no 6. What is this probability? What do you think? So how many pairs are satisfying this condition? Number of pairs which are satisfying this condition, that sum is 2 and there is no 6. I think only one pair, right? Only one pair is satisfying this condition. When the sum is 2 and there is no 6, so it is 1 upon 36. So you just see, I mean, you can just list out all the pairs, right? See here, you can do one thing. You can just list out all the pairs and just see how many of the pairs are satisfying these conditions, because every probability is equally likely, right? So which means you can say that if you just list out all the pairs, okay, which means 1 1 1 2 1 3 1 4 1 5 1 6, like that, right? So if you just list out what is the probability of this pair, the probability of this pair is 1 by 36, the probability of this pair is also 1 by 36, and so on. Now you just tell me how many of the pair are satisfying this condition, this event, okay, or this condition that sum is 2 and there is no 6. So I think this pair is satisfying and only this pair is satisfying, right? There is no 6. How many? 25 pairs, right? So that's why you can say that this probability is 25 upon 36, this probability is 1 upon 36, and finally you have, if you just divide it, this will be 1 upon 25. So you can say that you can find out this particular probability instead of, if you don't want to work with the reduced domain, then you can find out this particular probability using the original sample space also, which means you can use this formula and it will be 1 upon 25 only, right? Okay. So each of these probability is actually 1 upon 25. Now, what you can do, you can say that, okay, let's just work with the reduced sample space, which means if you don't want to work with this, you can work with this. That's okay. Like, which means this formula looks good. For you can run from 2 to 12, or if you want, you can run from 2 to 10 only, because 11 and 12 anyway will be zero probability. Because, okay, let me just show you. So basically, let's just do one thing. Let's just find out this expectation. Okay, but before finding out this expectation, is this conditional probability fine to everyone? Because we need to find out the conditional probability, then only we can find out the conditional expectation. So this conditional probability fine to everyone, because the conditional probability will lead to the conditional expectation only. Okay, so let's just see how to find out this conditional expectation. Now, this is the formula that we have got. Now this is equal to 2 into, okay, or maybe s into any of this. Okay, any of this is having how much probability? 1 upon 25, right? Any of this. Okay, but here the values of s are actually till 10, which means, okay, let me just tell you. See, this is, if s is 2, then what is the probability that sum being 2? I think 1 upon 25. If s is 3, then what is the probability that sum being 2? I think 1 upon 25. Similarly, if s is, let's suppose sum is 10, right? See here, if the sum is 10, right? Which means this one. If the sum is 10, then what is the probability of this sum? I think 1 upon 25, right? So these probabilities we know, that till 10 we know, which is, if this is 10, then this is 1 upon 25. If the sum is 11, then what is the probability that sum is 11 and there is no 6? There is no 6. Still sum is 11. What is the probability? It is 0, right? It is not possible. It is not even possible. So what is the probability that sum is 12 and there is no 6? It is not even possible. So that's why it is 0. Anyway, you don't need to do all of this. Like I just told you, maybe little lengthy way. So what you can do, you can understand that, okay, this is the reduced sample space, right? Now they're just asking for now you can understand this, that in the reduced sample space they're asking the expectation. Okay, so earlier we used to ask the expectation in the original sample space. Now we are asking the expectation in the reduced sample space. So which means this is 2 into 1 to 1 upon 25, just like the previous way. Okay, 2 into 1 upon 25, 3 into 1 upon 25, like that, right? Okay. Uh, so sorry. So see, this 2 is occurring with 1 and 1, right? But how many pairs, with how many pairs you are getting this 3? Is this 1 upon 25 or 2 upon 25? Yes, it should be. Uh, Yeah. So it should be, I think, 2 upon 25. With how many pairs you are getting? 4. I think 1, 3, and 3, 1, right? So again, 2 upon 25, right? With how many pairs you are getting? 5. I think 3, 2, you are getting it here. You are getting it here. And you will be getting 2, 3. I think this will be something else. Okay. So these probabilities are actually varying. Okay. It is not having the equal probability, but let's just see. So these probabilities are actually varying. So basically you can see here that uh 2 you will be getting, I think 25 they are dividing at end. Okay, that's fine. So 2 you will be getting with 1 upon 25, 3 you will be getting with 2 upon 25, 4 you will be getting with 3 upon 25. So you can calculate it. Okay, 5 you will be getting with 4 upon 25, like that, right? So for example, here 2 you will be getting, let me just ask you. So you will be getting sum s2 with how much probability? Sum is 2, only this pair, right? If sum is 3, then I think 1, 2, and then 2, 3. Two pair. Sorry, 1, 2, and 2, 1. So two pairs. If sum is 4, 1, 3, with 2, it will be 2, 2. Okay. So basically, these are the two pairs. And now you can flip this 3 also, 3, 1, right? Okay. If sum is 4, 5, then 1, 4, 2, 3. With 3, it will be 3, 2. With 4, it will be 4, 1. Okay. If sum is 6, then 1, 5, like that, right? So like that, you can find out the probabilities. Actually, it is not always increasing 1, 2, 3, 4, 5. It is not always increasing. You will see that, okay, it will be the symmetric, which means, let me just tell you quickly. If sum is 6, then it will be, I think, 2, 4, and then this is 3, 3, and then this will be 4, 2. Okay, and then this will be 5, 1. So if it is 1, then next is 5. If it is 2, then 4, 3, and then 3, 4, and then 2, 5, and then 1, right? If sum is 7, 1, 6, 2, 5. Okay, 1, 6 is anyway not possible. Okay, in the reduced domain, 6 is not there. So even you just forget about it. In the reduced domain, you don't even have the 6, right? Okay, so it is 2, 5. You can consider that dice only have 1 to 5. Okay, in the reduced domain. So this is 3, 4. This is, if this is 4, then this is 3. If this is 5, and then this is 2, like that, right? Okay, these are the again 4. Okay, so now it will be 3, like that. Okay, it will be anyway decreasing. So for example, if sum is 8, then this will be 4, 1. With 1 it is obviously not possible. With 2 it is not possible. With 3 it will be possible, right? 3, 5. With 4 it will be possible. 4, 4. With 5 it will be possible. Okay, 6 is anyway not there. So see here, 1, 2, 3 pairs, 4 pairs, 5 pairs, and then again, uh 4 and 1, 2, 3, 4, 5 pairs, and then again 4 pairs, and then 3 pairs, like that, right? Okay, so you can see that till how much you will be getting? 10, right? So if sum is, let's just quickly find out all the values. If sum is 9, then how many pairs? I think with 3 it will not be possible. With 4 it is 5. With 5 it is 4. If sum is 10, then with 5 it is 5. That's all, right? If sum is 11, sum cannot be 11 with only 5. So these are the only possible values. So basically, if sum is 2, then the probability is 1 upon 25. These must be total 25 pairs. Can you quickly count? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 plus 5, 15, plus 4, 19, plus 3, 22, 24, and 25, right? So these are the probabilities. Okay. Now you have the probabilities. Now you want to find out the expected value of the sum, given that there is no 6. Okay. Which will be, if the sum is 2, then it is 1 upon 25. If the sum is 3, then it is 2 upon 25. Like that, right? If the sum is 4, then it is 3 upon 25. Sum is 5, then like this, right? So you can find out the expected value of this sum. Okay. So one thing you notice here is that you need to basically find out the conditional probabilities, right? The conditional probabilities. And once you have the conditional probabilities, it is easy to get the conditional expectation. Okay. So the final answer is coming out to be 6. Great. Now let's just see more example. Probably you will be more familiar after those examples, right? For example, let's just do this question. So you roll two-sided dice D1 and D2. Let X be the summation. Okay, two six-sided dice. Okay, so again they are rolling two dice. Okay, D1 and D2. Let X be the summation of D1 and D2. Whatever the outcome of the first dice is, let's suppose D1. Outcome of the second dice is D2. Now they are saying that let Y be the value of D2. Okay, if the on the second dice, if this is 6, then X is actually, okay, X is actually the summation of X is sum, right? Then they are saying what is the expected value of the sum if on the second dice you are getting 6. Can you do this? Just do this with the reduced domain. So on the second dice, if you're getting 6, then on the first dice, what are the possible values of the first dice? 1, 2, 3, 4, 5, 6, right? And the possible value of the second dice is, fortunately, they have just very reduced it. They are saying this is 6. Okay. I mean, they have just reduced it. So only pairs, these are the possible. So at D1 plus D2, which is just X, what is this? 7, right? 8, 9. So let me just draw a line even. 9, 10, 11, 12, right? So these are the possible values of the sum. Now, what are the probability? What is the probability of this? What is the probability of this? 1, 2, 3, 4, 5, 6, right? This is the 1 by 6 probability. This is also 1 by 6 probability, and so on, right? So these are the 1 by 6 probabilities. Now, can you do this? So this question I have taken from Stanford. Just try out this. So what is the answer you're getting? Just sum all of this and then divide by 6. Okay. So for example, this is the answer that you will be getting 9.5. Okay. So they are saying which intuitively also making sense, which means that on the second, if you have already got 6, then 6 plus expected value that you are getting on the first dice. Okay. Expected value of the first dice is actually 3.5 only. Okay. So they are saying it is also intuitively making sense that, oh, if the second dice is 6, then you are directly adding 6 anyway, right? Have you understood this question? Let me know. Okay. Now let's just solve this question. Okay. This is not related to dice, but it is a general question. Suppose that x and y are the discrete random variable, like they are only taking, let's suppose, the values 1 and 2, such that the probability that they have given the joint probability, okay, that x is 1 and y is 1, it is 1 by 2, 1 and 2. So they have given, I think, all the possible values of the probabilities, right? Okay. Can you just check if these probabilities sum up to 1? So this is actually 5 upon 10. Okay. So 5, 6, 7, and yeah, these probabilities are summing up to 1. Okay, great. Because in the joint probability, do you remember, if you write the joint probability in the tabular form, then all the values here, summation should be 1, right? Summation of all the values. So we have seen this in the previous lecture. Okay. That do you remember we were finding the value of C? C means that, let's suppose, some of the value, one of the values C, then what is the value of C given this joint probability distribution? The easy examples that we have done, right? Okay. So any probability distribution doesn't really matter whether it is joint or conditional or any. Okay, and everything is a probability distribution. Okay, which means this is also the probability distribution. So for all the possible values of x and y, the summation should be 1. For example, if they write like this, sorry, the probability of x, let's suppose y equal to 2. Okay. And then probability of x being, let's suppose, could be anything, x being 1, 2, like this, right? Then do you think the summation of all the probabilities here, if you keep on changing the value of x, this y is fixed. Okay. Let's suppose this is fixed. If you keep on changing the value of x, will the probability summation will be 1? What do you think? See, what I'm saying here is that let's suppose you have a tree. Okay. Tree, and then you are saying, okay, let's suppose y is 1. Okay. And y could be, let's suppose, 2. Now here, uh x value, let's suppose x could be 1, x could be 2, x could be 3, like this, right? Now tell me, what is this notation? This is probability of x being 1 given that y is 2, right? What is this notation? This is probability of x being 1 given that y equal to, sorry, x being 2 given that y equal to 2. What is this notation? This is probability of x being 3 given that y is 2, right? Okay. Do you think all of these probabilities is 1 if you sum all of these probabilities? Yes, right? So if you sum all of these probabilities for any branch, it will be 1, right? Okay. So everything is actually the valid probability distribution only, right? I mean, even if you write the joint probabilities, which means probability of x being 1, comma y being 2, if you sum up all of these probabilities, which means what is this probability? If let's suppose this is x, value of x, okay, x could be 1, x could be 2, x could be 3. Now what is this probability? This is probability of x being 1, y being 1. Similarly, this is probability of x being 2, y being 1. So if you sum all of these node probabilities also, what do you think what you will be getting? Again, you will be getting 1. Okay. Again, you will be getting 1. So, so if you sum any valid probability distribution, you will be getting 1. Now tell me, if you sum these probabilities, these edge probabilities and these edge probability together, will you be getting 1? These edge probabilities and these edge probability together, will you be getting 1 again? No, right? It will be actually 2. These are the two different probability distributions. Okay. Okay. Should I write this, or you have already, seen these in the previous lecture? So I think you have already seen. Okay. So these things will keep on coming. Don't worry. We will be having more examples with these things. Okay. You will get more clarification. So let's just do this question. Okay. Now just check, if you sum all of these joint probability, are you getting one? Yes, you are getting one, right? Now, let's just solve this question. They are asking the expected value of, you know, this random variable x, given that y is one. Okay. So for that, what you can do as a first step, you can find out the conditional probabilities, which means what is the conditional probability that x, this conditional probability distribution actually, right? Which means what is the conditional probability that x being 1, given that y being 1, what is this value? What is the conditional probability that x being 2, given that y being 1? Okay. You can just first find out this, and then we will see that how to solve this question. Okay. As a first step, let's just find out the conditional probabilities. Okay. So what is this probability? This will be, can anyone tell me final answer? Okay. So Samir is saying it is 7 by 6. Let's just quickly verify. Okay. This is 1 by 2 divided by y being 1. Y being 1 means you need to, I think, add both of this, right? This is 5 by 10. This is 1 by 10. This is 6 by 10, right? Finally, this is 6 by 10. So it is 1 by 2 into 10 by 6, which is 5 by 6, right? Okay. So I think 5 by 6 is the answer. Can you verify this? Yeah. So 5 by 6 is the answer. What about this? X equal to 2, probability of x equal to 2 comma y equal to 1, given divided by probability of y equal to 1. So 2 and 1. So 2 and 1 is there. 1 by 10 divided by 6 by 10, right? So it is 1 by 6. Okay. Anyway, do you need to really find out this separately? No, right? For the conditional, this x has the only two possible values, which is y and which is 1 and 2. So if one of them is 5 by 6, then another one will be anyway 1 by 6, right? One, and like the another one will be anyway 1 by 6. So we have got 5 by 6 and 1 by 6 as the probabilities, which means I can say this is the probability which is 5 by 6. Okay. This is the probability which is 5 by 6, and this is the probability which is 1 by 6. So we have got these two probabilities. Now let's just see how easy it is to find out the expectation, given that we already know the probabilities, right? Conditional probabilities. Okay. Let's just see. So they're asking to find out this particular, expectation. Now, what is the answer? Expected value of x, given that y equal to 1, is actually the probability summation over all the possible values of x, and then x into probability of x only, right? X being x, you can write x being x, probability of x equal to x, or x being x, given that y is 1. So this is x may be 1 into this probability 5 by 6 plus x may be 2, right? X may be 2 into this probability, which is 1 by 6. Okay. So I think it is 5 plus 2, 7 by 6. Okay. So 7 by 6 is final answer. Yes. So Samir is saying he has told 7 by 6 as the final answer. Okay. Great. Okay. Understood. So these conditional probabilities are, conditional expectation is easy. It is just that we are finding out the expectation in the reduced domain, if you want to understand like that, right? Okay. Once you have the conditional probabilities, then finding out the conditional expectation is very easy. Let's just do more examples so that you are more familiar, right? Okay. So 7 by 6 is the final answer here. Let's just do this question. So what they are saying, consider the joint probability distribution, probability mass function given by the following table. So y value could be, let's suppose, 10 square, or it could be 10 power 4. X value, suppose it could be these four possible values. Okay. Now they're saying find out the expectation of x, given that expectation of the random variable x, given that y is 10 square, and also given that y is 10 power 4. Okay. Let's just do this question. So before solving this, let's just quickly find out the conditional probabilities, right? So if we find out the conditional probabilities, then conditional expectation will be very easy. So what is the conditional probability that x being, let's suppose, okay, let's suppose anything, okay, x being, okay, maybe I think we need to find out all the probabilities individually, right? So let's just find out x being 0.01, given that y being 10 square. So it will be the joint probability, which is 5 upon 12, divided by y being 10 square. So what is the probability that y being 10 square? This is 10 upon 36. See, this is 15 upon 36 plus 10 upon 36 plus 5 upon 36. So this is 20. Uh, Sorry, this is, yeah, 20 plus 10, 30, right? So this is 30 upon 36. So then this will be 6 upon 36, right? Okay. So this is 30 upon 36. Now that's how you can find out this particular probability. Similarly, you can find out probability of x being 0.1, given that y is 10 square, right? Okay. So you can find out these probabilities, and then you can find out this expectation. So let's just see. Okay. So see here, they have not shown, I think, the calculation. So they are saying this is 1 by 2. What is this 1 by 2, 1 by 3, 1 by 6? So what you are getting here? So this is 5 by 12 multiplied by 36 by 30. Okay, this is 1 by 2. So I think this first probability is 1 by 2. The probability of x being 0.01. So this is 0.01. This is, I think, 0.1. Then this is 1, and so on. Okay. So these are the probabilities 1 by 2, 1 by 3, and 1 by 6. Right. So they're asking you to find out the expected value of this particular random variable on this condition. So this is coming out to be 123 divided by 600. Okay, this is coming out to be 123 divided by 600. How we calculate it? This is the probability of x being sorry. This is the probability. This particular thing is a probability of x being 0.01, given that y is 10 square, right? So we can find out this probability easily, which is coming out to be 1 by 2. Like that, you can solve this question. Can you solve this question? Do you think this is tough? No, right? So I think you can solve this question. This is easy question only. So the answers are here. You can even verify the answers, right? Okay. So these are the two expectations which are being asked, which is expected value of x given that y is 10 square, expected value of x given that y is 10 to the power 4. So these are the two things that has been asked. Now, what is the expected value of x with no condition? So this is something that comes under total law of expectation, which we will see anyway tomorrow. But for now, can you try to guess that what it could be? So what I'm trying to say here is that you have got, let's suppose you have got uh, expected value of x, given that, let's suppose y has only two possible values. Okay, let's suppose 1 and 2. Okay, given that y being 1, suppose you know these things. Okay, you know the expected value of x, let's suppose, given that y being 2, and someone asks you what is the expected value of x. Okay, what is the expected value of x? Then you will say it should be logically, it seems like we will see it anyway tomorrow. This is called total law of expectation, but logically it seems like the expected value of x, given that y is 1, into probability of y being 1, right? Y being 1 plus expected value of x, given that y being 2, into probability of y being 2. Do you remember this? This formula, we have already seen this little bit, not much, but little bit. Do you remember? When I introduced the total of expectation, do you remember I said it is something like this: expected value of, x, given that a some event, and then probability of a, plus expected value of x, given that uh, a complement, into probability of a complement, something like this. In the tree method, when I was introducing tree method. Okay, let me just show you. Okay, give me a second. Let me just show you. Okay, so I think you can see my screen. So here, in this particular, this is one of the lecture we have already seen in module 1. So here we have seen that the law of total expectation looks something like this, right? So it is just an intuitive way that, okay, this is expectation. Even I have not written it as a conditional expectation, but it is actually the conditional expectation, which means this particular thing, okay, which like intuitively we have seen this, but in this module 2, we will see this more formatically, right? So which means that this particular thing, we have seen that here I was saying E1 and E2, which means the expectation of x is nothing but some expectation, which means the expectation of x given that the probability of a, okay, this E1 is nothing but conditional expectation, which means x given that the a has already occurred. This E2 is nothing but the expectation of x given that a complement has occurred. Okay, do you remember this slide? Little bit you might remember, right? So these things we have seen, and on based of that, we have seen multiple questions. So for example, this question like this, right? So we have seen multiple question on based on that. How many of you remember this particular tree methods and these things? Okay, so for example, this is E1, E2, like that we have seen. So these were the conditional expectation only, right? So these were just conditional expectations. Okay, now let's just continue. So basically I was just saying that if you have, let's suppose these conditional expectations, then you can write like this. So which means you are saying this is some expectation E1 into the probability of some event A plus expectation E2 into probability that the event A hasn't occurred. Okay, so if you have these two expectation and someone asks you to find out the expectation of X, then you can actually do it, right? So for example, in this particular example also, they are trying to do this. So if I write like this, okay, so if I write like this, then can you tell me can you tell me what are the values of this fill in the blanks? So what should be this fill in the blanks? It is which probability of, can you tell me y or x or what? Can anyone tell me what should be this probability? Yeah, probability of y being 10 square, right? Similarly, what is this probability? Probability of y being 10 is power 4, right? Okay. This is called total law of expectation, which we will see again. But here I'm just telling you, a glance. So this is called total law of expectation. Okay. Or law of total expectation. Okay. So you can call it law of total expectation or total law of expectation, doesn't matter. So for example, this is law of total expectation. Okay. Okay, we will see this again, but I'm just telling you quickly here. Now let's just see more examples. Now, before I go to more examples, let's just look at this expectation as a this conditional expectation as a function of y, which means you might have noticed one thing here, that we are getting two values, right? We are getting two values of this expectation of x, which means it is depending on the value of y. For example, just a second. If let's suppose by being 10 square, then the value is coming like this. If by being 10 is power 4, then the value is coming like this, right? So these are the two independent and different values. Okay, which means this expectation of any random variable x, given that y being maybe small y, then it will be a basically a number, or it will be a function, which means it will be a number depending on this particular value y, right? So which means this whole thing is a number, but it depends on this value y. Is this okay to everyone? So you can say, can I write it like this? G of y. Can I write it like this? Which means you can say it is just a function depending on the value of y. So you can treat this as a function. So this is just a function of y. Okay. So this by the way I've taken from Stanford University. Okay. So what they're saying here, let me just write it. See, they are saying here is that, okay, they are saying that this particular expectation that we have seen, it depends on the value of y as an input. For example, it might so happen that if y is 5, then this expectation is 12. Okay. For example, if y is 3, then the expectation is 6. So you can consider this expectation as a function of y, right? So this is a number. I mean, if you just find out the expectation of x, this is a number, but this is a function of y. Okay. Again, this is a slide from Stanford. Let me know if that is okay to everyone. Okay. So this is also the slide from Stanford University. So this is a number y because this expectation doesn't depend on any random variable. Okay, we used to see if this is a this is just a dice. So in that case, the expectation comes out to be. Do you remember? It is 3.5. If it is a dice, right? The expectation of x. If x is the random variable that shows the output of the dice. Okay, but if you are writing like this conditional expectation, then it will depend on this y. So we can call it g of y. Okay, which is a function of y. Okay, depending on this value it will be some other value. Okay, now if you write expectation of x equal to, let's suppose, 5, then this doesn't make sense. So basically this is an event. Okay, you can't find the expectation of the event. Okay, so we find the expectation of the random variable. Maybe it is x, maybe it is the conditional the conditional thing, but you can't find the expectation of the event. Okay, so we don't find expectation. Okay, that is already written. Expectation of event. So for example, we find out the expectation of the random variable, and we find out the expectation of the probability, expectation of the event. Sorry, the probability of the event. So which means the probability. If you're writing the probability, then it should be the event. If you're writing the expectation, then it should be the random variable. So for example, does this make sense to write expectation of, let's suppose, x being 1? Does this make sense? No, right? Does this make sense? Expectation of any event? No. These things doesn't make sense. Okay, doesn't make sense. Similarly, if I ask you, does this make sense to write the probability of x? You don't tell. Okay, you don't tell whether it is 1 or 2. Just this. Okay, the probability of x. It doesn't make sense. Okay, so doesn't make sense until unless it is event, right? So you can write it like this. Probability of x being small x, you can write like this. I mean, this is okay to write the shorthand notation, but generally it is like this only. If you want to find out the probability of any random variable without assigning any value, then it doesn't make sense. Okay. Okay. Now let's just see this question. This is a to e, which means the value could be here. This could be either the value or could be the random variable. One random variable function of y, one random variable function of x. Okay, let's just see that which one is which one. So this expectation of x, is this a random variable? Samir is saying the conditional expectation is also giving the number. Yes, it is giving the number, but it is depending on the y. So for example, as we have seen, this will be finally a number. Obviously, it will be a number only, but it is depending on the value of y. So if I write the small y here, then I can say it is a function of y, right? So depending on this value, you are getting your answer. So that's why it is. You can say it is a function of y. Okay. So, so what is this A? This one is, okay. Just tell me one is. You can write your answer like this. One A. Okay. You can type like this. So this one is A, I think. Right. What about B? Expectation of, okay, we will see this. Okay, we will see this expectation of joint distribution, I mean x comma y, we will see this. Okay, let's just come to the C. Expectation of this, maybe x plus y. What do you think? This is again a random variable only, so I think this is A. What about this? So see here, I'm not assigning any value. Okay. If I'm not assigning any value, it means they are saying that, okay, this is basically that they want to keep it as a function, which means they are saying this is depending on the value, right? What value y takes, it will be that thing only. So this is, if I'm writing, okay, the notation wise, by the way, it is again from Stanford University only. Okay. So so if I'm writing like this, then this notation means they are saying it depends on the value of y. So it will be one random variable, it will be a function of y, right? So I think this is B. What about this? This is, I think, A, right? What about this? What about this? Yes, this is E. Actually, it doesn't make sense to write the expectation of an event. What about this? Yes, this will be a value, right? Okay. So let's just see. Yeah, this is a value. It doesn't make sense. This thing was A only, right? So I think 5 was A, and 4 was B. Okay, 3 was A. Yeah. So actually these things doesn't make sense. So I will tell you. Okay, I will tell you this. These things doesn't actually make sense. Expectation we find out of any random variable. This x comma y is actually not a random variable, right? So that's why it is E. It doesn't make sense. So x comma y is actually not the random variable, right? Expectation, we want to find out the expectation of any random variable, right? But this x comma y is not a random variable. Now what about this expectation of x? This is just A. Okay, so it was easy question only, but I hope you got it. Okay, so what is the difference between 4 and 5? See, this 4 is saying expectation of x given that y. Actually, they're keeping it open, which means they're saying depending on the value that y takes. Suppose that y is taking some value, okay, some value 3, then this will be something. Okay, if y is taking 4, then this will be something. So they're not assigning the value of y. So it is depending on the value of y, right? So it is just like that. It is just like that. That you find out the probability of x given that y equal to 2, right? If you find out this will be a number. Okay, just like a notation I'm telling you, if you write like this, probability of x given y, will it be a number? Will it be a number? This is actually conditional probability complete distribution, right? So this is a probability distribution. Yes. So in 4 we can take any value of y. So that's why this is a function, right? Okay, just like this, just like this. I think in the last lecture we talked about this also, right? Now let's just see this question. What they are saying: for each of the following, identify whether it is a random variable or just like a value. Okay, I mean, we have already seen this one type of example. This is another type of example. So this is little more tricky. Actually, these things, expectation of expectation, this again comes under the total expectation. So maybe you can leave B and D, or maybe we can do B and D. Okay, but the little bit intuitive idea, you can try to do this B and D. Anyway, we are going to see this again under the law of total expectation. Okay, expectation of expectation comes under the law of total expectation. Okay, we have already said, like, we will cover this in the next lecture, but for now let's just do all of this. Okay, I mean, you can keep this B and D optional, okay, for now, but at least just let's do all of this. Okay, except B and D. So what about this A? This is this is, I think, a value, right? A scalar value basically. Okay, This, okay, let's just leave it for now. What about this? This is actually a function of random variable, which is again a random variable. Okay. This is actually function of x or function of y. So, so it will be the function of x, right? It will be function of x or y, function of y, function of x. So function of a random variable is also a random variable. Do you remember? Function of, okay. What about this? What do you think? This is a function of uh, x, function of y, and so on. What do you think? No, they are not assigning any value. So, I mean, they are not saying probability of x being, what is the probability of x is taking two, given that y is taking two, something like this, right? They are not saying something like this. Okay. They're just saying like this. Okay. This is just a notation. So basically, this is, you can say, depending on that, what is the value of y, what is the value of x. So function of x and y. Okay. Which is a random variable only. What about this? This is the function of x or y. Right. This is a function of y. What about this? This is this is the value, right? Okay. Intuitively, do you want to guess this? So this is what? A value or what? Tell me. This is a value. Inside is a value. If you take the expectation of 5, expectation of any value, for example, expectation of 5, then what it will be? It is just 5, right? Expectation of any constant is just the same constant. So finally, you can say it is nothing but, this is nothing but expectation of y only, which is a value. Why it is expectation of y? Because it is a constant. So expectation of any constant is just a constant. Okay. Anyway, do you want to guess this? So inside is a function of x. Inside is a function of x. If you again take the expectation, okay, for all the possible values of x, actually we will see this, but a little bit intuitively you want to guess. So inside is a function of x, but ultimately it will be the value. Okay, the whole thing is a value. We will see this, okay, later on. Intuitively you can understand like this. Inside is a function of x. Okay, you are having a random variable here, right? You are having a random variable x, I mean random variable of function of x. For example, you can say you are having something like this, expectation of y being y given x, right? So this is nothing but expectation of function of x. Is this okay to everyone? Which is a value, right? Yes. So you can understand like this. Anyway, we will see this again. Okay. We will see this again. Don't worry. But you can understand like this. Expectation of this. This inside is a function of x, and the expectation of any function or any random variable is just a value, right? So it is a value. Okay. Now let's see more questions. So there was a question that we have already done. For example, if we are saying that if we, toys are, if we toss our dice, if you roll two, okay, there are two dice. If you are rolling two dice, d1 and d2, x is the sum and y is the value of d2. Then we have already solved it. Okay, we have already solved it that if y is 6, which means the d2 is 6, then what is the probability, what is the expectation that of this sum, which means the sum value could be, if this is one of them is 6, then it could be 7 to 12, right? So we have already solved it, right? We have already solved this thing, we have already done, right? This is already done. Now they're asking that instead of y being 6, can you find out the expectation of x, given that y is taking any random value? For example, y is small y. Can you do this? So for example, instead of 6, you will be writing small y. So what is the probability that x being small x and y being small y, given that y being small y? Just just try this question and let me know if you are finding the answer or not. Just take 1 minute and try out this question, okay? Okay, Rashri is getting answer as 7. No, answer should be the function of by only. Okay. It is not a constant answer. It should be the function of by only. So it is not 7. Should be the function of by. Okay. So let's just see this particular question. So what they're saying, that find out this the value of the expectation of x, given that y is some constant. Okay. So basically they are saying that, for example, this x is the summation of d1 and d2, right? So they are saying that expected value of d1 plus d2, given that, for example, d2 is this y basically, which is d2 only. Okay, small y, right? Okay. So this is what they're asking. Actually, we will see this later on also, but here you might be knowing about the linearity of the expectation. So in the conditional expectation also this follows, which means we will see these are the properties of the conditional expectation. Okay, so which means that this plus this. Okay, so in the conditional expectation also the linearity follows. Okay, so d2, given that d2 is y. Is this okay to everyone? Now, from here, let's just try to solve this question. Now, what you can say, that tell me, is this D1 and D2 independent or these are dependent? These are independent, right? So if these are independent, again, okay, we will see with the properties also. If these are independent, actually it is very easy to prove that this is nothing but expectation of D1 only. Okay. If D1 and D2 are independent, then it doesn't really matter that you are taking the expectation with respect to D2, D2 is something. Okay. Plus, if D2 is y, then this is nothing but expectation of D2, and D2 is actually y, right? So which means this is just a small y, which is just a small y, and then this is expectation of D1. So here you can say that you have solved this question, or you are going to solve this question using the multiple properties, which is the independence property and the linearity property. But I'm just giving you the heads up, okay? And we will see these properties, and then we will be solving multiple questions, which are complex questions also. But for now, I'm just giving you the heads up that yes, you can apply the linearity here. And if these are independent, if D1 and D2 are independent, then it is as good as writing D1. You can easily prove it. Do you want to prove it? So just imagine the formula of this, right? It will be the it will be like this. All the possible values of, you can say, D1 into the probability of D1 given D2, right? D2 equal to pi. So this is nothing but the probability of D1 only. Okay. D1 being, let's suppose, small d or something like that, right? Okay. So ultimately this is just a probability of D. And then this whole thing is nothing but a expectation of D1 only. Okay, like that you can easily prove it. So if D1 and D2, or the two random variables, are independent, then expectation with respect to another random variable is actually the same expectation, unconditional expectation basically. Okay, then what is the expectation of D1? It is 3.5, right? 3.5 plus y. This is the answer. It was easy question, to be honest, but here you just need to see that if you can apply the property of linearity. Okay, this is the property of linearity, property of linearity, and this is independence property. Okay, so Sonam is saying, can you explain this again? Okay, see here, that we want to find out the expectation of D1 plus D2, given that D2 is some value. Okay. For example, it is y. This is the question. Now you can apply the linearity property here, which means it will be d1 given d2 equal to y plus expectation of d2 given d2 equal to y. Okay. Now, after linearity, you are applying which property? Independence property. If d1 and d2 are independent, which means these two dices are independent, then you can say this is nothing but expectation of d1 only. Okay. Plus expectation of some random variable, given that the random variable is itself is fixed. So which means expectation of y only. Okay. Some constant, which is y. So here, this is 3.5. You can calculate it, which means it is very easy to calculate, right? 1 plus 2, 2 plus 3 plus 4 plus 5 plus 6 divided by 6. Okay. It is very easy to calculate that this is 1.5. And then this is y only. So 3.5 plus y is the answer. Now, this question might seem tough because of the two properties that I haven't told you explicitly, but I have included this particular question just to give you the heads up that we are going to see the property now. Okay, so which means that we have applied two properties here. What is the first property? This is the linearity of expectation. This is independence, right? Okay, independence and conditional expectation. Okay, so these two properties we have applied to solve this particular question. So 3.5 plus y is the answer. Let's just see if the answer is matching. Yeah, y plus 3.5, right? Okay, which is a function of y. Now, let's see this question. So what they're saying, if we are rolling two six-sided die, okay, again, d1, d2, the same thing. Let's suppose s is the sum, right? Okay, Rajshri is asking, what about the values of y given in the question? No, in the question, they have not given the value of y. I mean, they're just saying that y can take 1 to 6. Okay, y can take any value from 1 to 6, which is a common sense thing. I mean, they have written, right? Okay. So now let's just solve this question. Now they're saying what is this expectation of sum given this d2? Okay, I think we have just solved it. So what is this, by the way? There is a function of s, function of d2, function of or it is a number. What is the answer? And also, can you give the expression? So I think answer is B, right? It is a function of d2. So yeah, answer is B. It is a function of d2. And for the expression, you can solve it like this. So which means I think it was 3.5 plus d2. Okay, we have already done this. Okay. So now let's just solve more questions. Let's solve this question. Okay. This question I have taken from Utah University. Let's see what they're trying to say. So they're saying this is actually a tricky or difficult question, or I can say lengthy. Okay, bit lengthy than compared to what we have already seen. Okay. It is a bit lengthy question, by the way. Let's just solve this question. They are saying an urn has three balls, numbered 0, 2, 0, 1, 2. Let x be the number on a randomly chosen ball. Then we flip x fair coins and y be the number of heads. Okay. So they are saying that you are flipping x is the number of fair coins. Okay. Number of fair coins you are flipping. And y is the number of heads you are getting. And there is some basket, you can say. Okay. Here you have three balls, right? These are the three balls. One of them is numbered at 0, another one is numbered at 1, another one is numbered as 2. Now what we are going to do, let's suppose let x be the number of randomly chosen ball. Okay. Okay. So we are going to first, randomly choose one ball, and then what we are going to do, then flip X fair coins. Okay. So then we're going to flip X fair coins. For example, if this is coming out to be, the ball you are drawing is, let's suppose it's coming out to be 0, then you don't flip any coin. You flip one coin or you flip two coins. Okay. Then they're asking the joint PMF given in the table. Okay. Sorry. The table is actually on the next page. I forgot to write it there only. Okay. So this is the joint PMF. Let's suppose this is given. Here, right? Okay. If this is not visible, let me just write it like this. So this is the joint PMF which is given. Now let's just see that what they're asking. Okay. So they're saying the joint PMF is given. Then find out the expectation of X given the Y. Okay. Let's just first try to understand this joint PMF. So X is what? X is the randomly chosen ball, right? So the randomly chosen ball could be either 0 or could be either 1 or could be either 2. So the value of X could be 0, 1 or 2, right? It could be either 0 or could be 1 or could be 2. Now, what is Y? Y is the number of heads. So obviously, like the number of heads could be 0. If you're tossing, let's suppose at most two dice, then it could be at most two, and again it could be 0, 1, and 2. So this is the joint PMF, let's suppose, which is given. So which means that if you are rolling no, let's suppose you're not rolling any coin, which means X is 0, then what is the probability that, for example, this is the probability that they are saying that you are not rolling any coin, and then Y is the number of heads, right? You are getting 0 heads. So this is 1 by 3. Okay. Why that is 1 by 3? Because you first draw, right? So maybe let me just tell you. See here, the probability of X being 0 and Y being 0. This will be, you can say, what is the first event? The X is the first event or the Y is the first event? I think X is the first event, right? I mean, you first draw the ball. So you can, write it like this, right? I mean, I'm writing like this because X is the first event. So I'm writing on the condition on the X. Okay. So what is the probability of that X being 0? It is 1 by 3. What is the probability that you don't flip and then you don't get any head? What is the probability? 1, right? If you don't flip, you will not be getting any head. So it is 1 by 3 probability. Okay. Just tell me what is the probability of, let's suppose, X being 1 and Y being, maybe let's suppose, 0. So this is again probability of Y being 0 given X being 1 into probability of X being 1. Tell me what is the probability that X being 1? It is 1 by 3 into what is this probability that X is 1, which means you are basically tossing one coin and then you don't get any head if you toss just one coin. What is this probability? 1 by 2, right? Yes. So total probability, this should be 1 by 6. So X being 1 and Y being 0. X being 1 and Y being 0. This is 1 by 6. Now you can actually find out all of these probabilities if you want to. Okay. So for example, what is the probability of X being 2 and Y being 2 or Y being 1? Can anyone tell me what is this answer? Probability of X being 2, comma Y being 1. If you want, you can understand with the tree method also, because X is the first event. So X could be, you can say X could be 0, 1 and 2. And then if you're not flipping, right, then what is the probability that you will getting 0? It is a probability, this is Y, right? So this is the probability 1, this is the probability 0, this is the probability 0. So Y being 0, Y being 1, Y being 2. These are the probabilities. Anyway, you can do this using the tree method also if you want to. Okay, list out all the probabilities using the tree method. By the way, just tell me what is this probability? This is probability of y being 1 given that x being 2. So what is the probability that x being 2? It is 1 by 3, right? And based on that, if x is 2, which means you are basically x is the number of coins, right? See here. Now x, then you flip x number of fair coins. So if you're flipping 2 coins, what is the probability you get exactly one head? So you can get head tail head, and tail, right? Exactly one head. What is the probability? 1 by 2, right? 1 by 4 plus 1 by 4. So into 1 by 2. Again, this is 1 by 6. So x is 2, y is 1. Let's just check it. So this is 1 by 6. Okay. So you can anyway fill this table. Maybe this may be because I have not written the table here. Now they're asking you to find out the expectation of x given that y could be anything. Y could be 0, y could be 1, y could be 2. Okay. So expectation of x given that y. They're asking you to find out this. Okay. Let's just find out this separately. Given that y is 0, expectation of x given that y is 1. Can you do this? So suppose if you want to find out the expectation of x given that y is 0, then how to find out it? You will be saying it is nothing but summation of x only, x into probability of x being x given that y being 0. Okay. So x value could be 0, 1, 2. And I think all of these conditional probabilities are okay to everyone, right? Because to find out the conditional expectation, we need to know the conditional probabilities. So these conditional probabilities, I hope this is okay to everyone. So these conditional probabilities are already found, right? So once you find these conditional probabilities, then you can actually find out this conditional expectation. So let me tell you the answer directly. Okay. So for example, for x equal to 0, so for y equal to 0, if you have the conditional probabilities with you, then this is 4 by 7. Okay. Okay, you have the joint probabilities, and then from the joint probability, you can find out the conditional probability. 4 by 7, 3 by 2, and 2. Okay, this is the answer. Now, let's suppose you got this answer, right? Is there any difficulty in getting this answer? Tell me. So this is easy, right? I mean, this is not very tough. Now, let's suppose you have this answer. Can you find out the expectation of x? It will be expectation of x given that y is 0 into probability of y being 0 plus like this, right? Plus two more terms. So if you want, you can find out this, okay? If you want, you can find out the expectation of x given these expectations, okay? Plus expectation of x given that y is 1 into probability of y equal to 1 plus expectation of x given that y is 2 into probability of y is 2. Okay. Anyway, this is called a law of total expectation, which we will see. Right? Okay. Now let's just see this question. So what they're saying that suppose, okay, these are the three variables they have. Now in this case, okay, the PMF is given like this. Okay, the joint PMF is given. Now they're asking you to find out the expectation of this and the expectation of this. This is little more interesting or little more tough. Okay. Do you want to try this as an homework? We can solve this question tomorrow if you want, and just try your best. Okay. Just see that if there are multiple random variables, then how to deal with this. Okay. I mean, this is not a very tough question. This is also easy question only. Here you will be having like, I mean, this is just, condition on some event basically, right? So you can say here the probability of X given that, I mean, the probability that you will be using will be something like this. Okay. So just try this out. Okay. So this question, the solution of this question is on the next page. Just try out this question. And if you try this, if you solve this, then your concept or your, practice will be more, you can say you will be having the more practice, and then you will be more confident actually to solve these kind of questions. So just try out this question, and the solution is on the next page. Okay. Just try out this question as an homework. Is this fine? Okay. Okay. Just try your best, and the solution is on the next page. Now, let's just see the conditional expectation in bit more detail. So basically, now we are going to see the properties of conditional expectation. Law of total expectation. Okay. For now, we have seen the conditional expectation on the discrete random variable only, but we will see the conditional expectation on continuous random variable now. Okay. Conditional. Okay. And then we will see many examples. Conditional expectations. Okay. So once we finish all of this, then the conditional expectation and law of total expectation, this particular topic will be finished. So all of this we will do tomorrow, and then we will be starting a new topic. Okay. The new topic will be, I think, for now, I cannot say 100%, but I think we are going to start after that covariance and correlation. Okay. After that, most probably, I will be starting covariance and correlation. Okay. So thank you, everyone. Thank you so much. So we will be starting this tomorrow. Okay. Thank you. If you have any doubt, you can just let me know. Okay. So if you have no doubt, then we can just end this class. Okay, great. Thank you.